Hi, Mami.
Hi, Francisco.
Hi,
Hi.
how are you?
I am great. How are you?
I'm doing fine. There is the sunshine today in Amsterdam, so it is definitely a great day. You never say no. You never are sad when there is sunshine in Amsterdam.
Yeah.
Where are you at the moment?
I am in India, still
Okay.
waiting for my semester to start.
Yep.
Yeah.
Yep. Indeed, I can take back what I was saying before you were entering the call. So basically, I was introducing you. I said you obtained your bachelor degree in electric and electronics engineering, right? And you have recently been awarded a teaching assistantship, so sort of a scholarship, to participate in the master program in physics at the University of Massachusetts, right?
Yeah.
Yes, that is great. That is very great to hear. And of course, I wish you all the luck for that. So yeah, I said we today we were going to talk about the life cycle of stars. So
Yeah.
yep, that's. I also said that we try to make an outline of the question, and we had to, due to time reason, we had to rule out some points because otherwise we would need another episode to talk about also even the other points. But yeah, I would say we can get into it, and yeah, I wanted to ask you first. So we have been here around for relatively a short amount of time, whereas stars have been here. We have traces of stars from billions and billions of years ago. How is that possible? How do we know so much about stars?
So adding to your question only. So imagine stars they live for millions and billions of years, like you said, right? And we came along and we are looking up at these stars, and maybe we took some pictures, and now we know how they were born. Like, isn't that crazy? It's same as me looking at you, and I say, okay, Francisco, now that I've looked at you, I know how you were born. Like, isn't that crazy? So, yeah. So we know. So there are many, many stars, not just one star. So that's where star clusters come in. So what happens is that the star clusters are like a group of stars. So there are some clusters that are relatively younger and some that are old. So we have different types of clusters. And so what we do is we study them separately. So for example, if I see a star, and I have seen already a lot of stars and their phases. So I say, okay, this star looks like something which is gonna transition into that particular type of stars. And that's how a lot of categorization has been done, and a lot of studies have been performed, and we have made out this HR diagram, which is the Hertzsprung-Russell diagram, in which we study this evolution of stars beautifully. Like that's how we do that.
Okay, okay, that sounds very cool. But then let's go to the let's say to the origin. How stars? You said I can look at you, Francesca, and I may say, okay, this is how you were born. But how does a star born?
So how stars were born? So for that, let's talk about life on Earth. So we know that we need metabolism. Right, we have metabolism, right? Life on Earth has metabolism, and it also has reproduction. So these are the two things that are required in order to sustain life on Earth. So now, if I were to say that stars also have metabolism, in a way, they take birth, they live their life, and they die. So what happens is after they are dead, so they form gas clouds. All right. So out of those gas clouds, they wait for the enrichment, and then other stars are born out of it. It's a cycle. Now, to talk about, okay, how do we make stars, or how stars are born really? So we need to talk about galaxies a little bit. So galaxies, if I say broadly, we can categorize them into two types of galaxies. First is elliptical, and the second is spiral. So elliptical galaxy, as the name suggests, it's elliptical in shape and it's comparatively round. And in that galaxy, there's barely any gas. So which means, so that galaxy has used up all of its gas in its evolution, throughout its evolution. But if I talk about spiral galaxies, so they are comparatively flat and they have these spiral arms. So an example of spiral galaxy is Milky Way, the galaxy we are in right now. So yeah, so this galaxy, as I was saying, has a lot of gas comparatively. So what happens is there are these gas clouds, a lot of gas clouds, all right. And so these both type of galaxies, they are of roughly same age. They are as old as each other. Again, I'm speaking very broadly. But again, they do have some gas clouds in it. So these gas clouds, right? That's where stars are born out of. But then talking about these gas clouds, so they are just moving around the galaxy, minding their own way, living their life happily. But then, yeah. But then what happens is something happens. Now that something could be maybe a star died nearby, and that because of the death of that star, it produced certain shock waves. That's one reason. So this something happened, and the other something could be spiral density waves. All right. So these are two things that can happen to these gas clouds. So,
okay,
yeah.
with spiral density waves, to illustrate it very briefly in more simpler terms.
Okay, so I'll give you an example. So I saw this video of Neil deGrasse Tyson recently. So he gave this beautiful example, which sort of sums up what spiral density wave is. So that wave is actually, so imagine you're stuck in traffic, all right? And there's this car which is moving very slowly. Like it's obviously very annoying. But apart from that, the other cars, they have to move according to that slower car. So that slower car, imagine it is the density wave, all right, the spiral density wave. So the other cars, they are moving slowly, but they would try to find a way, somewhere from the other side, maybe to come out of it. Yeah. So this density wave is that slow car, which is, in that molecular cloud. All right. So did that give you an idea?
Yep.
All right.
Yes.
So yeah. So this is what happens with the with the gas clouds. So these two shock waves as well as the density wave, they make the gas cloud contract, or it contracts the gas cloud. So when it contracts, some of the regions, they become denser. It becomes denser a little bit. So if it is becoming denser, it will have a lot of gravity as well. So imagine if something is denser, it will have a greater gravity than the rest of the region. Yep. So imagine I am that dense thing and I am gaining more gravity. So more gravity breeds more gravity. So what happens is there are small molecules around me. So I would just pull them up towards me as well, making me more dense. And I would then have more gravity. Okay. So yeah, it's somewhat like that. So since I started first, there will be no other region that would be more denser than me, or would have more gravity than me. Like, so that's the core. Okay. So yeah. So this
which we find the core at the, I would say, at the center, right, of a star.
So core is in the center.
Yeah, at the center, we find it, right?
Yeah.
Okay.
Yeah. So this gas cloud becoming denser and having more gravity, it begins. So this is the beginning of star formation. This is like the beginning. So now I told you about clusters, right, in the beginning. So there are a lot of stars which form out of one gas cloud. So these star clusters belong to the same gas cloud. That's why they share the same birthday, because they're born together and they have same chemical composition, and yeah, they are very near to each other. So that's there. And talking about, like, again, coming back to the molecular clouds. So when they're becoming denser and they're triggering star formation, there's a point where in the core, the shock, something happens, and that something is thermonuclear fusion. So the ignition of it happens. So ignition is like starting a car, we ignite it. So the starting of it. So that happens, and that's where the stars are formed, out of that ignition, and other stuff is happening after that. But yeah, to sum up your question,
when we have nuclear fusion, so we do have the beginning of the process of formation of a star when the star starts with nuclear fusion. So
exactly.
Okay.
Yeah.
Okay. So that's how a star born, very briefly, very concisely. Okay, but what is then happening inside a star? You say, okay, it is nuclear fusion, but first of all, what is nuclear fusion, and how does nuclear fusion composes, let's say, make up of the main body of life or star?
Yeah. So thermonuclear fission, if I just look at the name, thermo means heat, right? Thermo, we can connect it to heat, and nuclear is the nucleus, and fusion is like I'm bringing together two nuclei to form one nucleus. That's what fusion is. So now what if I combine certain quantum mechanical effects with the periodic table, right? So I will get heavier and heavier elements. Like the mass of those elements will increase. So these gas clouds, all right, they are made up of hydrogen and helium. So when a star is evolving, it needs to form higher mass elements. And that's where nuclear fusion comes in. So nuclear fusion helps in the making of higher mass elements. So again, repeating what I said, if I combine quantum mechanical laws with periodic table, I can achieve that. Like I can form higher mass elements. Now, so there's one interesting thing as well. There's one thing is fusion, that is bringing together of nuclei to form one nucleus. And there's also nuclear fission, which is splitting of atoms, right? And both of these processes, they release energy.
Okay, one question. What do you when we have nuclear fusion, which nuclei are we putting together? And when we have nuclear fission, which nuclei are we splitting? Is that
all right? So inside a star, just nuclear fusion is happening. And I'll come to like what is happening after this. So with fission, I'm just trying to get to a point here. Like I'm just bringing up a new thing. Fission is not happening inside a star as of now. So just fusion is happening, but I'm coming to a point. Like I'll get back to your question after this.
Okay.
So So with fission, we are splitting the atoms, right? And fusion, we are doing opposite. We are combining two nucleus to form one nucleus. I said it opposite. We are fusing two nuclei to form one nucleus. Yeah. So both of these processes, they are releasing energy, all right? So as we move above the periodic table, which means we are going to heavier elements. So they are releasing less and less energy. Did you get that? Like they're releasing less and less energy, and in the fusion, they are combining and climbing up, and in fission, they are splitting and combining up. But both of them are releasing energy. So what's like the middle point of it? Like where does it stop, right? So there's a point in periodic table, or an element in periodic table, which is called iron. So when it reaches till iron, right, both of these processes. So iron, what it does is, he's like, okay, no can do, bro. I am not gonna release any energy. Instead, I'm gonna take yours, and then I'm gonna either fizz or fuse. All right. It doesn't release energy, it absorbs.
Okay.
Yeah. And it doesn't let fusion and fission to proceed any further.
Okay. So iron is our, let's say, element cap at which we do not produce any energy anymore. Is that right?
Yeah. So iron, it's not producing. In fact, it's absorbing energy to perform these two processes.
Okay.
And yeah. So there's this breaking point, iron. Now, coming to your question, nucleosynthesis and what's happening and what's fusing together. So what happens? So helium cloud or these gas clouds, they're initially and essentially made up of hydrogen and helium, as I said. So initially, hydrogen is combining to form helium nucleus. Hydrogen combining to form helium. So it's not that easy. So a lot of things are happening. There are a lot of pathways in order to do so. So it's not just hydrogen combining to form helium. They can go to boron. There's also production of boron, beryllium decays to form helium. A lot of things are going on, but we're not going to that. So hydrogen is, we're just saying for now that hydrogen combines to form helium. And there are a lot of other pathways as well. Now, as I said, the heavier elements are also forming, right? So how does that form? So what if I combine 3 atoms, 3 nuclei of helium? So helium has atomic number 2. If I combine 3 of those, 2 into 3, 6. So I'll have atomic number 6. And 6 atomic number belongs to carbon. So carbon will form, right? So again, it's not that easy. A lot of things are going on inside and we're not going to that. So that's what is happening basically. Fusion is happening. And like how carbon formed, a lot of other heavier elements are forming, like nitrogen, oxygen. Yeah. So these different heavier elements, they form outer layers around the core of the star.
Okay, and they are constantly forming that. Well, nuclear fusion is like I once watched a video saying, imagine we have the core, and on the core there are industries. Outside the core there are industries of nuclear fusion, and they are constantly making nuclear fusion and generating these heavy elements which covers the core. Is that accurate?
Which form the outer layers.
Okay.
Yeah. So moving forward, again, why does even like a star needs nuclear fusion, you might ask? It needs nuclear fusion because it needs to have an equilibrium. So what happens is, there's this star, right? This is a star, and so there's this gravitational pressure from the outside, which wants the star to collapse, collapse.
Basically, it's gravity, the gravity of the gas cloud.
Yeah, it wants the star to collapse.
Okay.
All right. And now that's where fusion comes in. Fusion is like, I won't let the star die. I won't let it collapse. So the fusion, there's a lot of pressure because of fusion. So fusion is applying a force outside. So that's how, there's an equilibrium. And it's not just any equilibrium, but they are stable. Like they are stable.
So they are stable because they can last for billions of years. So apparently they are stable,
yeah. But there's also a trick to it. Like, so what if, again, to continue as to what you said, so what if hydrogen runs out? Because hydrogen is going to run out, and all of these elements, they are not going to last forever or for billions of years, right? They're going to run out at some point of time.
So basically, what I would say, translated the question is, what happened when the main fuel of the nuclear fusion runs out? Okay, because nuclear fusion starts from the hydrogen, right?
Yeah.
Okay, so what happened when the fuel of a star runs out?
Yeah. So if hydrogen runs out, so as I said, there's gravity also, which is applying like an inward force. It's like gravitational pressure. So now gravity wins, right? Because hydrogen is finished now. So gravity is collapsing the core. So in the core, what is happening? The temperature and pressure is increasing, right? It's getting smaller and smaller and denser. So temperature and pressure are increasing. So now helium is like, okay, now I have enough energy to perform fusion. Helium kicks in now. So helium is like, okay, I will save the star now. I will be performing fusion. And it is releasing energy now, helium. Hydrogen has run out. Now helium is like, I'm the boss. I'm gonna provide star with the energy. So now again, the core is smaller, but still helium is there. And now helium is providing enough energy to become this, to let the star become stable now. Right
Okay.
now, it's stable again because helium has come.
Okay, so basically we are nuclear fusion with hydrogen, then nuclear fusion runs out, is the cores of the star starts contracting. When it starts contracting at, let's say, a certain point, helium kicks in and says, I will be doing nuclear fusion, and helium provides for a new equilibrium. And the stable becomes stable, and the stars become stable again.
Yeah.
Okay.
So again, stable. But, and this again, this lasts for quite some time. And so what if helium also runs out? You know, again.
Kind of a mess. Kind of a mess.
Yeah. So because helium is also, it's not going to last forever. It's going to run out at some point of time. It can't provide energy for star like for millions and billions of years. It's going to run out. So now what happens is, now the heavier elements, more heavier elements like carbon comes in. Now, first of all, what will happen? The gravity again wins because helium is not there. So again, the core starts collapsing. Now temperature increases, pressure increases, and now carbon comes in. It's like, now I am going to save the star. So yeah, so carbon is there and it's fusing and releasing energy. And again, the star becomes stable.
Okay. Again. Okay.
And this goes on and goes on because carbon is also going to run out, then oxygen and nitrogen, and it comes till iron now. This is happening continuously because these heavier elements are also running out. Now I'm directly jumping to iron.
Okay. Right. So we are reaching the phase where where a star is trying to do nuclear fusion with iron after it has run out of all the, let's say,
the other heavier.
Okay. Yeah. Okay. What happens with iron then?
Yeah. So now the star is again collapsing, gravity winning. It's again becoming even smaller. Temperature and pressures are increasing at a high rate. And there's iron. Now, what did I tell you about iron? Like, it's not gonna release any energy. It absorbs, to fuse. That's what I told you, right? So it's like, okay, bring me any energy. I'm gonna take it all, and then I'm gonna fuse. I'm not gonna provide anything to you. I'm just gonna take your energy. That's what iron is doing. So now, what will happen is the question. So it's like a complicated process, but so imagine it's collapsing and collapsing because gravity is still winning. Iron is not providing anything. Like there's no pressure because it's collapsing, right? Iron is absorbing all the energy. So star is collapsing and collapsing, and it reaches a point where it explodes.
Okay. So basically now we are entering the phase of death of a star, right?
Yeah. Like we're coming to the death. Yeah. Okay. The beginning of the death of the star.
Of a star. Okay. So it happens, iron cannot produce nuclear fusion, and so the core explodes.
The core collapses so much that that it explodes, right? It explodes. And this explosion is known as supernova explosion.
Okay.
So yeah. So this is the death of the star, which I mentioned initially, that causes the shock waves in these gas clouds that form new stars. So it's all related. Yeah.
Yeah. And when it explodes, what which elements does it eject into the, let's say, free space?
Coming to that. So they have all the heavier elements, right? The core, everything is there, right? So now the outer layers were also there. So now this all explodes. So the gases, they spread across the galaxy, like everywhere. So what happens is, so this shock waves, and there are these gases that spread and they form new stars. And these new stars now have these heavier elements that were in this present star, which underwent this supernova explosion.
Okay.
Yeah. So these heavier elements are present already in this gas. And the new stars which will form now will have planets with heavier elements. For example, carbon, oxygen, nitrogen. They will have
why these other stars will have planets around?
And that's how it's formed, right? So out of these gas clouds as well, planets are also formed out of the gas clouds. So okay. Planets are formed with the star. They have this disk, the big disk. Sometimes planets are formed and sometimes not. Like it depends. So this shock wave and this gas that spread around will enable some of the stars to have planets that will have these heavier elements: oxygen, nitrogen, and carbon. And they are the basic needs, basic requirements or ingredients that we need in order for a life to sustain. And that's how we come in, the life is formed, and we are literally made up of star stuff or stardust. So we live in the universe, and the universe is alive within us, in a way. So yeah,
this is amazing to hear. This is it's I don't know, at least to me, when I hear this kind of discussion or this kind of explanation, I really am mesmerized by how on a larger scale everything is much more connected than what we actually think. Okay, so when people say some time ago, I would hear people saying, yeah, but we are made of the same material as the stars are made, and I said, wow, how can it really be possible? And that is just why that is possible. So it is really fascinating, that I believe.
Yeah, it's crazy how these things happen. This particular quote that we are made of star stuff, it just is so fascinating in itself, right? So this quote itself, it makes you question a lot of things. Like your friend, they told you about this stuff, and you may wonder, like, how is this possible? Stuff like that. And you start researching about this stuff, and it brings you here.
Yeah. Okay. So yeah, I think that was with regards to the death of a star. But do we have because of course we know that stars are not every star is not of the same mass, as the same mass. So are there any distinction of for the death of a star, during the death of a star, based on the mass of that star?
Yeah, I completely forgot to cover this point. So supernova explosion, it happens in high mass stars. All right. So if I have
with the high mass, what do we mean with the high mass?
So our sun, it's like a medium-sized star. If I were to compare, so our sun, it will never go supernova explosion. Like, okay. What it will instead become a planetary nebula. So what will happen is its outer layer will expand, and it will eventually form a white dwarf, and then will cool down and will form a black dwarf. Like, I could elaborate it on it a little bit. So I told you about iron, right? Iron is left inside the core. So it undergoes, since it cannot release energy, it undergoes something called iron photodisintegration, if I'm not wrong, if this is the term. I'm completely forgetting. Yeah. So what happens is iron then it absorbs energy and it forms a lot of helium nuclei, and it also forms neutrons. Now this helium nuclei, they form protons, and there are protons and electrons present in the core which squeeze together to form neutrons again. So in the later evolutionary stages like white dwarfs, neutron stars, so they are essentially, their core is made up of neutrons mostly. So in a white dwarf, which our sun will be becoming, it will be made up of neutrons. Like fusion will not be happening, and it will be essentially neutrons in there.
Okay, and how does not gravity makes our sun, which will become a white dwarf? How does gravity does not, let's say, influence anymore? How can a white dwarf be stable, or a neutron star?
So gravity, so if I talk about gravity is playing a picture in stars like sun as well. But if I were to say, why is it not going supernova, if it's not going, it's because its mass is very high. Like the other stars, they have very high mass and they'll have high temperatures. That's why it's also said that high mass stars don't survive as long as the stars that are the mass of our sun, or even lower than that. So it's like that. And talking about the later evolutionary stages of high mass stars, they would either become a neutron star or a black hole. So so neutron star, if it depends upon the density. Now if the density is so high, the gravity is so high that even light cannot escape, then it will become a black hole. And
okay, and that's this distinction, let's say, from white dwarf to neutron star to black hole is based upon also upon the mass.
Yeah, mass.
Okay.
Mass.
Okay, yeah, so basically we have that. If I do remember, I think kind of correctly, up until 1.4 times the mass of the sun, a star collapsing should become a white dwarf. From 1.4 to 3 times the mass of the sun, the star collapsing will become a neutron star. So, and from 3 to 5 onwards times the mass of the sun, then the star will become a black hole. Okay, so this distinction then is based on the mass. Okay, sorry, go on.
Very cool. You've done your homework, everything. Yeah. Yeah, that's great.
Okay. And what is very let's say briefly, you said gravity is so strong that light cannot escape from a black hole. But why is that the case? How can it be happening? We know that Einstein in 1905 formulating special relativity said nothing can travel faster than the speed of light. So how can it be that something is actually stronger, let's say, is pulling inwards light? Shouldn't it be the absolute speed of everything within the universe?
So I want to deviate from your question a little bit, because so you mentioned that nothing travels faster than speed of light, right? So do you know the universe is expanding? The universe is expanding, and that expansion is happening faster than speed of light. So,
why is that the case? Why is that the case, that the light can travel, that we have something that can travel faster than the speed of light?
Could you repeat your question?
So basically, what I have been, I think it was either in Kip Thorne, Black Holes and Time Warps book. I think it was explaining the fact that we say, Einstein said nothing can travel from at a speed greater than the speed of light. But how is then that the universe is expanding at a rate which is greater than the speed of light? And he said at least this was the explanation. I also heard some other videos on YouTube. Is that when we say nothing can travel at the speed of light, can travel faster than the speed of light, we have to say add the little word locally. So we need to add a word after, which is locally. Nothing can travel faster than the speed of light locally, so within the universe. Einstein told us, formulated special relativity and then general relativity, as a revolutionizing our understanding of space and time. And he said that space is not, let's say, a different thing from time. They are a continuum, a 4-dimensional, let's say, continuum that, let's say, goes on. I like to think about it, how I like to think about it, sort of a dot that starts getting bigger. Or also, this is a similarity that I read a lot in books. Imagine to blow a balloon. You have a balloon, okay, and you start blowing. Basically, that's pretty much it. Inside the balloon, nothing can go great at a speed greater than the speed of light. The speed at which the balloon is expanding, okay, so at the speed at which our universe is expanding, can go greater than the speed of light. So that was that was why the thing I was asking.
Yeah, so the balloon thing, if you put certain dots on it, then you can actually observe, those dots will move away from each other, and that's how it's really happened. And there's one more example of it. If we bake a bread and we put some chocolate chips in it, it's nearer initially, but then after baking it expands and those chocolate chip distance increases. Yeah, there are a lot of fun examples.
I didn't know about the chocolate chip. Okay.
Yeah.
Okay. Yeah, that is okay. That is very exciting to me to be talking about this. But yeah, the last point I wanted to ask you maybe is, how did you, if you have, let's say, any suggestion for students who would like to have let's say a similar path as you, also getting to reach a position where you are funded from a university and then you are able to continue your studies, not having to pay extremely high tuition fees as in the United States, but you are actually getting paid. How did you do it? Because I personally am interested into this. So maybe this question is more for me than other people listening. But yeah, how did you do it?
Yeah, so the mantra is to stay curious and to research a lot. Because if you're going to apply to these university and if you want scholarships and if you want assistantships, you need to know your stuff. You need to know it. The first point is to polish your knowledge and to know the things you are applying to. So how I got it, it's very funny actually. I didn't apply for it at all. So so US universities, they just see your application and then they decide if they want to give you a scholarship or not. And the assistantship thing was, I didn't apply for it, and there was the professor, the graduate admission director, who approached me if I am interested in this thing. So we had a little interview, and and yeah, I think I did impress him in that interview. And it relates to how much internships I think I have done, despite being from the engineering background. I actually I never did internships in my background, at all. I was mostly studying about physics, astrophysics, and doing internships for the same. And I have been an educator for various Indian space startups. So that's what I also told him in that interview sort of thing. And I think he liked me and my interview.
Apparently, yes. Otherwise, but what was the, let's say, the subject or content of the interview? What were you asked? I don't know, either technical question or a background or I don't know, anything?
I was asked my background also. So
Okay.
he got to know that I'm from engineering background and I want to switch. So they don't usually give you scholarships if you do that. But then again, I mentioned about what I have done in past 4 years in my engineering time period. So I had a lot of on-field exposure. So that's what I told him as well, because I conduct these stargazing sessions and I teach kids about the same. So that's what I told him as well.
Okay.
Yeah.
Okay. Very nice. Then, Manvi, I think I will have to let you go. Otherwise, I will you will sue me for not making you be able to carry out your task for the day. But that was a great pleasure for me. I could keep on going for the whole afternoon. I really have no hurry to talk about this. But again, thanks a lot. Thanks a lot for being with me. And of course, best of luck for the new exciting chapter of your life at the University of Massachusetts, doing the master in physics.
Yeah. Thank you so much. And as much as I would love to spend my evening talking about astrophysics, but I do have some stuff to complete. So I'll get back to it as well.
Yeah.
Thank
Thanks
you
a
for
lot.
having me.
No, thank you. The pleasure was totally mine. Okay, then I think this we can wrap it up for this episode. And thanks for whoever listened. Thanks for being with us.
Thank you so much.